very much for coming out today to hear us talk about ML Ops using GitHub Actions and Kubernetes. My name is Jeremy Lewi. I am a tech lead at Google. I work on Kubeflow, which is an open source Kubernetes native platform for machine learning. And I'll let my co-speaker introduce himself.
Hi, my name's Hamel. I'm a machine learning engineer at GitHub.
All right. So let's get started. So when most people hear about AI, what they think about is a lot of very high-profile and very exciting success stories in terms of AI. So you have self-driving cars like Waymo. You have AlphaGo, in which a computer program beat the world's best Go player. You have everyday applications like Google Translate. But when ML engineers and data scientists who are in the field think about AI, they have a very different experience and life story. So this Twitter quote has been receiving a lot of attention in the ML infra and data science community because it really sums up pretty nicely the sentiment and feeling of a data scientist on a day-to-day basis. And the idea is basically data scientists are able to rapidly and quickly develop a model and prove that this model is able to improve some important business metric, and then they would try to get that into production or into some application, and that's where they run into roadblocks. So they end up spending months trying to get this into production, and oftentimes they fail. And what we've learned at Google is that one of the reasons that these systems is so difficult to get ML into production is that when you're building an ML application, you're actually building a complex distributed system. So this is a famous diagram from a paper that Google published called the Hidden Technical Debt in ML Systems. And the key idea is that most people tend to think about ML as being about complex machine learning algorithms and difficult math. But in reality, this ends up being only a small portion of your ML application or system. In reality, what you have is a lot of systems and infrastructure that surrounds that and is necessary to support that ML algorithm. So for example, you need infrastructure to collect data and pre-process it, extract features. You need to clean the data and make sure that it's valid and you can use it in production. You have to manage all of the resources, like the compute, in order to do both the training and the serving. Once you get your model into production, you have all of the usual ops challenges, monitoring, logging, auditing, et cetera. And so in reality, most of your time and energy goes into all these surrounding systems and infrastructure, and that's what makes getting ML into production so difficult and so challenging. So one of the things that we've learned at Google dealing with complex distributed systems is that if you deploy more often, this often reduces the likelihood that problems will occur, and it also reduces the severity of the problems when they do happen. So this has been backed up by research. So there's a DevOps research report called the DORA report that comes out every year. And in 2019, the data basically confirmed this conclusion, that if you deploy more often, you will have less problems. And this is a key principle of Google SREs. So the quote on the bottom right is from a paper that Google SREs published. And it's basically about how important getting to automation that allows you to do things like push on green is in order to maintain some of the most complex systems at Google. So for traditional applications, continuous integration and continuous deployment has a very rich ecosystem. So we have this cycle where we want to do development, make a change to our application, like our web application, push that to our source repo, then build it, test it, and deploy it. And so we have a very rich tool chain for supporting that. So if, for example, we can develop our code in VS Code. We have lots of integrations in VS Code to do things like automatically build our code using a tool chain like Maven or Bazel. We then have integrations for gluing the steps together. So you have plugins for VS Code for things like Git. And finally, you have off-the-shelf platforms like Jenkins that can put this all together. For ML, CI/CD is similar, but it's different. And these differences create challenges which are preventing us from having a rich tool chain as of yet to help us do CI/CD for machine learning. So as an example, with ML, we have new tools. As an example, a lot of data scientists and ML engineers are using Jupyter, which is a notebooking environment, to develop their models, because it provides really rich visualizations and is really great for interactive data analysis. But these tool chain, right, like Jupyter, lacks some of the integrations that we expect from our existing tool chain. So as an example, we don't really have great tools with Jupyter to automatically build artifacts like containers that we would typically want to put into our CI/CD pipeline to automate the deployment and getting them into production. Similarly, when it comes to testing models, we have new challenges. So when it comes to traditional web applications, we have a pretty good handle on how we go about deploying that application and then testing it by sending an RPC to make sure that we get the desired response. And if we get the desired response, we know that the code is good, and we can push it into production. But evaluating a model is a little bit different, because what we care about is whether that model is actually improving the performance and quality of the predictions. And that can be a lot harder to evaluate. The first thing you have to do is you have to train the model, and that can take a lot of time, and it can also be computationally expensive. The other problem is that oftentimes, when you have a model like a ranking model or a recommendation model, it can be difficult to evaluate the performance of that model offline. You may have to deploy that model into production, test it on a subset of traffic, and see whether it's actually driving more traffic to see whether it's improving quality. So because of all these challenges, we don't really have a really great tool chain yet for doing CI/CD for ML. And as a result, this lack of automation causes problems. And Hamel's going to walk us through an example to illustrate how the lack of automation causes problems.
Thanks, Jeremy. So I just want to show you an example, a concrete example of what happens because of this lack of DevOps for machine learning, or more concretely, CI/CD for machine learning. This is a real PR from the Kubeflow project. And this is really indicative of the PR that you will see on any machine learning project. It's very typical. And this specific person opened a PR, and they said they're changing some parameters of a model. So changing the size of a default, the size of a hidden layer, changing the learning rate strategy, the type of model, so on and so forth. And later on in this PR, someone makes a comment and says, did these new parameters and things you changed, did that increase the performance of the model? And so in this case, precision and recall. And the original author responds and says, yes, I think so. And the PR gets merged. So this is really problematic. For a traditional software kind of development lifecycle, we don't want to guess whether a code should be merged or not. So you might typically see on GitHub, when you're using CI/CD, you have your integration test, smoke test, a unit test, whatever they might be, and you have these robust systems that help you monitor that, so you don't have to guess, like I just showed you in that PR. And so we want to bring that same paradigm to machine learning so that you can take the guesswork out. And then there's a lot of other things. So you want to be able to block PRs from being merged in production, for example, if the test didn't pass, or if the test is not even run, which we also want to bring into machine learning. So what can we do about this? So I'm going to show you a demo of how we can use GitHub Actions and Kubeflow, which is a cloud-native machine learning infrastructure project, to orchestrate a machine learning CI/CD workflow. And what I'm going to show you is we're going to start with opening a PR. Then we're going to build the environment. We're going to train the model on Kubernetes using Kubeflow. And we're going to collect metrics about the model's performance. And then we will ultimately deploy that model. And then along the way, we will report back status of all of these steps into the PR so that it's transparent and it's easy to understand the end result. So I'm going to go ahead and show a demo. So what I have here is a PR example. And in this PR, I'm changing some parameters of a model. So if you look at this file, I'm increasing the size of an embedding layer from 50 to 85. The details are not important, but the idea is I'm changing something about this model. And for example, one thing that you may want to do differently from traditional CI/CD is you might not want to trigger a full run of your model on every push, because machine learning can be very compute intensive and time intensive. You might want a human to give the final word on when they're ready to run the full test. So using GitHub Actions, we can orchestrate something like chat ops. So I'm going to issue a command here, run full test, /run full test, make a comment, and that will trigger GitHub Actions to start its process. So what you'll see next is we'll start building the environment. So I'm going to click on the Actions tab, and then you'll see this workflow. And the first thing we're doing is we're building the containers that contain this code in this PR. And we're going to use that to then run the machine learning workflow on the infrastructure of our choice. So in this case, we're building the containers. They're being pushed to the Docker registry that we have. And then we're building the Kubernetes spec that will then deploy this machine learning pipeline to Kubeflow to get run. And so if you notice, the context for this is dropped into the PR. So Actions build a container, and it submitted the job to Kubeflow to run this machine learning pipeline. I'm not going to go into a lot of detail right now about how that works. Jeremy is going to tell you more about Kubeflow. But this is sort of a machine learning workflow system that runs on Kubeflow. Again, this is available from the PR. And as you notice, we created a check run. So this yellow dot here is going to stay open until the end of the machine learning job. So eventually, this job will keep running. The training will complete, and it'll clear that check run. Now, keep in mind, this is running on the infrastructure of your choice. In this specific example, this is running on GKE, but this can run anywhere. This can run on any cloud of your choice, on any infrastructure of your choice. And when the model is complete, when the training is complete, it'll clear that check run. So now that check run is complete. And you might notice there's some more information that has been dropped into the PR. So while the model was training, we logged a lot of statistics to an experiment tracking system. In this case, we're using weights and biases. And that experiment tracking system captures lots of information about model performance and other system metrics that you might want to see. What happens is when the model is done, it queries that and brings it into the PR. So this is what weights and biases looks like. You can use any experiment tracking system you want. But just to give you an idea, this is a system where you can log various detailed metrics about your machine learning model's training run, things like things that are logged to standard out, and you see here various model artifacts. So again, this is dropped into the PR. So all runs that correspond to this SHA that this PR is run on is dropped into this PR. And it's dropped in as Markdown. And you can customize this. Actually, all of these steps are available as actions that you can use on the marketplace, which I'll show you how to get to a little bit later. And you can verify that this run is not stale, that corresponds to the latest SHA on the head of this branch. And so you might take this information, and this will allow you to have a discussion about the model's performance, and it allows you to have a transparent record of everything that's related to this model in this PR. And it really takes out a lot of the guesswork that you otherwise might have. So finally, you might want to deploy this model. So we can use ChatOps again. So you see, I'm going to take this run ID and then use ChatOps to deploy this model. And this specific demo is linked with the GitHub deployment API, so we can report status on how this model is deployed. Now, using this demo, this is being deployed to Google Cloud Functions, which is a Lambda-like service. And this is just to drive home the fact that you can have various heterogeneous deployments using actions, because actions can allow you to string together whatever infrastructure that you want. And then you see that this has been reported back to the PR. So let me go back a little bit. So this shows that model being deployed. And then when it's done being deployed, it'll report back a success or failure of deployment into the PR so that you can go and see if this code was deployed and when it was deployed. And you can have a record of it all within the PR. And this is just the dashboard of this particular model being deployed to Google Cloud Functions. So this is really exciting. We showed here in this example kind of an end-to-end workflow where you have machine learning CI/CD. Model is running on the infrastructure of your choice. In this case, we're using GPUs on the machine learning infrastructure of your choice. And you can compose various GitHub actions to achieve that. And that's really new and exciting. That is going to allow more transparency for people working on machine learning and that are using GitHub. So you can see the example of this code by going to this link, bit.ly ml-ops, if you want to kind of dig in more. So I'll give it back to Jeremy so he can talk about Kubeflow and drill into that a little bit more.
Thank you, Hamel. So now we're going to talk about how we go about building that CI/CD workflow that Hamel just demoed by using Kubeflow and GitHub Actions. So let's start off by talking about what we need to do ML for CI/CD for ML. There's really 4 things we need. We need tools and applications that allow us to develop our models. That includes editing the code as well as training our models. We also need applications that we can use to deploy our models and create serving endpoints that we can hit with HTTP or gRPC requests. The second thing that we need is the third thing is tools for automation, right? So we need that PR workflow where we can automatically trigger those training and deployment steps like Hamel showed in response to actions by the user. And so for that, we're going to be using GitHub Actions. And then finally, what we'll need is we often want to have a manual review process where humans decide whether a model is actually improving performance and therefore decide to push it into production. And for that, we're going to use GitHub and the standard review and approval process. So let's start with Kubeflow. So what we started to see about 2 years ago in the ML space was that companies that were really successful with machine learning and were really on the cutting edge started talking a lot about the platforms they were building, in particular to solve this problem about how to continuously integrate and deploy models into production. So Google was one of the first, and we started talking about TFX, which was our internal machine learning system, which we've started to open source. And one of the key problems that TFX was designed to solve was continually retraining your models as new data arrived and pushing those models into production. But other companies also started talking a lot about the platforms they were building. Lyft was one of the big ones. They talked about a platform called Lyft Learn, which enables their data scientists to rapidly develop models using Jupyter notebooks and then push those into production. But a lot of other companies like Bloomberg, Stripe, Airbnb have been talking about the platforms they've been building and how they've been building these platforms on top of open source applications like TensorFlow, XGBoost, and Onyx, and then also on top of Kubernetes. So we decided to start building Kubeflow as an open source Kubernetes native platform for machine learning so that all the companies that wanted to use and needed an ML platform but didn't have the resources to build their own platform could also get the advantages and begin to use ML successfully just like these bigger companies. So our mission with Kubeflow is to make it easy for everyone to develop, deploy, and manage portable distributed machine learning on Kubernetes. We are an entirely open source project. We have an incredible amount of momentum. So we have over 30 companies that are contributing and building on top of Kubeflow. And we have an amazing number of PRs and unique authors every month. So I think we're up to over 80 unique PR contributors every 28 days or so. So getting back to the CI/CD workflow, the first step is developing your models with Kubeflow, developing your models. And we're going to show you how Kubeflow makes that easy. So as we said before, Jupyter is becoming one of the standard tools in the data scientist toolbox. We had a panel a couple years ago at the Kubeflow Summit, and we asked a bunch of data scientists, what is the tool you most can't live without? And they all said notebooks and Jupyter. So with Kubeflow, we've made it super easy to spin up notebooks on Kubernetes. We provide you this very simple web UI where you can launch a new notebook and then begin to use that to develop your model. But as we showed before, one of the big challenges with Jupyter Notebooks is how do you go about converting those notebooks into artifacts like Docker containers that you can begin to integrate into a CI/CD workflow. And so for that, in Kubeflow, we've developed Fairing. And Fairing is an SDK that makes it easy to convert notebooks into Docker containers. And so the idea is that Fairing is divided into 3 steps. You have preprocessors. And what the preprocessor does is it basically takes your Jupyter notebook, which is really just a JSON file, and converts that to a Python file. And it basically does that just by sort of stripping out the markdown and then allow you to tell it, using various filters and other kinds of syntax, what cells to include and what cells to remove. So you can remove your visualizations or some of the other cells that you don't need in your production artifacts. And once you've produced that Python file, Fairing provides a builder, which makes it easy to build a Docker container from that Python file. And so it can do things like generate a pip file, a requirements file to install your Python dependencies. Then finally, once you have that container, we actually need to deploy that on Kubernetes. And so for that, Fairing provides deployers, which allow you to easily create Kubernetes resources using that Docker container that you've built. And so the idea here is that by building this SDK, we've provided the integration for you so you can integrate your development step with the downstream steps. So Kubeflow provides a variety of ways that you can actually execute these ML workloads on Kubernetes. And that's what these different types of applications can be used as the deployers with Fairing. So the first one is you typically want to train your model. And so for that, Kubernetes provides a bunch of different applications called custom resources that make it really easy to train your model using different frameworks like TensorFlow or PyTorch or XGBoost. And the idea here is that we give you a very simple declarative spec, so you can give us a very simple YAML specification that focuses on the high-level information that you as a data scientist want to provide. So in particular, you just have to specify the image, which is the Docker container that contains your code, and then you would have to specify the number of workers that you want to use if you want to run your job distributed so you can take advantage of training large models in parallel. And so this simplifies the management process because the data scientist no longer has to manage individual resources or multiple containers. They just have to create this simple Kubernetes specification. Another big challenge in machine learning is hyperparameter tuning. A lot of times, machine learning models or deep learning models have hyperparameters that the only way to train them is to try models with a bunch of different values and see which one performs best. So a simple example with deep learning is you often have the number of different layers to use in your model, and the only way to see what the desired best value is to try a bunch of different values. So with the hyperparameter tuning support in Kubeflow, you can, again, just create a very simple declarative specification in which you specify what algorithm you want to use to tune your hyperparameters, and then what the parameters are. And then the application will take care of launching multiple training jobs, waiting for those jobs to finish, collect the metrics, and then report back to you which model performs the best and what those desired parameters are. Finally, you actually have to deploy the model. And so for that, we provide KF Serving. And so KF Serving is an application where, again, one can provide a simple declarative spec where all one has to provide is the URI of your model. So this could be a protocol buffer outputted by TensorFlow. And then under the hood, KF Serving takes care of all of the complex DevOps tasks or MLOps tasks that you would need to actually deploy this model into production. So as an example of some of the complex DevOps challenges that KF Serving handles for you is KF Serving will automatically auto-scale the number of instances your model has deployed. So if you have a lot of requests coming in and you need to spin up more capacity, it'll automatically add more containers. And as the number of requests decrease, it'll reduce the number of containers you have deployed so you're not wasting resources or money on compute you don't need. It can also handle complex DevOps challenges like rolling out changes and doing things like canaries and rollouts. On the machine learning side, KF Serving provides a lot of advanced functionality. As an example, we provide model servers that can easily take a Python function that does inference and then wraps that with an RPC or REST server that integrates with things like Istio to provide monitoring and metrics that you need if you're actually going to deploy this into production. It can also handle things like inference graphs, where you deploy two types of models, such as an XGBoost model and a deep learning model, and then combines those results from both of those models to generate the final predictions. And then finally, it can handle things like A/B testing. So once we have these different applications, we actually have to tie them together into the complete workflow. And that's where GitHub and GitHub Actions comes into play. And so to describe that piece of it, I'm going to hand it back over to Hamel.
Thanks, Jeremy. So just to kind of circle back, and just in case anybody doesn't know what GitHub Actions is yet, probably everybody does at this point in the conference. GitHub Actions makes a lot of this stuff very easily. So just in case you haven't seen GitHub Actions, you specify it with the YAML file in the .github/workflow directory of your repo. You can trigger it on any GitHub event. And then you can also use other predefined workflows from other people without rewriting all the code. So it's very modular and composable in that sense. And that makes it really good for machine learning ops because you can inherit other people's parts of other people's workflow without kind of redoing it, rebuilding it. And there's a large library of existing actions, including some actions for machine learning ops. So you can find those on the marketplace. You can search for those. And also, they come up when you're building actions as well. I'm going to show you a screen with that. And if you go to the bit.ly link, bit.ly/mlops, which is the link I shared earlier, you'll see a list of actions that can help you facilitate MLOps to get you started. But the great part is, again, these are all very composable. So let's say you don't want to use Argo or you don't even want to use weights and biases. You can find another action that does that and compose your ML workflow in a different way. And adding actions to your repo, again, that's done by specifying the YAML file in the workflows directory, your .github workflows directory. And again, you can search the marketplace and find actions that are relevant to you. So that makes this problem very tractable of kind of connecting your code to your various workflows. OK, and just to kind of wrap things up and kind of discuss what we talked about. So again, we talked about how we started from a pull request, and then we build the environment from the code in that pull request, specifically Docker containers, and then showed a way how we can orchestrate training of those models with GitHub Actions and reporting the status back to the PR, and also at the same time collecting metrics about your model and reporting that back to the PR, and then ultimately deploying the model. And GitHub Actions is a great way to orchestrate all of these things. That's all we have for this talk, but here are some resources that you might be interested in, and we're also open to questions if you have any.